Alright, let's start with this last lecture. I thought that this last lecture would be dedicated to an overview of the applications of the formalism that we have studied during the last 3 lectures. So, when we talk, so now it's what I had written in the syllabus of this course. I started with lensing is today a major tool in astrophysics and cosmology, astronomy and cosmology. And this is indeed a tool that we use to do quite a lot of measurements in several regimes that are known as weak, strong, and micro lenses. They all allow us to extract information from our universe at different scales, and they tend to use the properties of lensing in different ways. So, of course, I'm not going to be very comprehensive about all those things. Each of them would require a full series of lectures. But I'm going. My goal here is to try to introduce you to give you a glance of what those words means and what we can do with them. This is the goal. And I will start with weak lensing. And with preliminaries, of course, about cosmology, because weak lensing is the application of lensing that has to do with cosmology in very large scales. And first, I have to talk a bit about homogeneous cosmology, light propagation in homogeneous cosmology. So this is what I mean here by cosmology. In homogeneous and isotropic cosmologies. So you know that the space-time that is the background model for cosmology, for homogeneous and isotropic cosmologies, is the Friedmann-Lemaitre-Robertson-Walker geometry. The FLRW, Friedmann-Lemaitre-Robertson-Walker geometry, which reads, if I write the line element, we write it like this. Theta squared plus theta squared. That's one of the coordinate systems with which we can represent the FLRW geometry. Fk being this function that depends, there is a way to write it actually just in terms of a hyperbolic sign, so it would be sine h square root of minus k chi divided by square root of minus k, or something like this. So k being the spatial curvature parameter of, so this would be the intrinsic curvature of the spatial hypersurfaces of the FLRW geometry. So I don't think that I have to introduce too much the FLRW geometry here, right? So this is why I'm not spending too much time on it. But the idea is that we would like to know, and of course A, the scale factor, etc. So we would like to know first how light propagates through this kind of universe, this kind of space-time. And for that purpose, a good thing is to use the property that I introduced in the first lecture, which is the conformal invariance of light propagation, the laws of optics. Use conformal invariance. And you see that, so I know that I can study light propagation So light rays and our geodesics are going to be the same. So they are the same as those of the conformal metric. Yes, tilde squared, where I just remove the scale factor. All right. And then what you can show, and this could be done as an exercise 1, is to show that so geodesics, null geodesics, converging to the observer at chi equals 0 satisfy first, well, just chi equal eta 0 minus eta, and theta phi equal constant. Yeah, so that's actually, so in terms of those coordinates centered on chi equals 0, then they are propagating as straight lines in terms of those coordinates. So if I have chi equals 0 and light rays. In particular, when you consider light rays that are converging to this observer at the center of the coordinate system, they are not affected by spatial curvature in terms of those coordinates. They are not deflected by, well, we don't have, this k does not matter at all. All right, so that is about light rays. We can also show that the frequency is also quite standard. So that the frequency evolves. Oh yeah, sorry, I forgot to say, this is the conformal time at observation. So that would be the conformal time today if we consider an observer that is observing photons coming today, providing today. So you can show that frequency decreases as the scale factor, well, the inverse of the scale factor. So that we have this very famous relation that the redshift is given by just the ratio of the scale factors of emission and reception. So it would be at all very standard. Now something which is a bit more interesting is what happens to it's omega emission over omega reception, but maybe. All right. And something which is a bit more interesting is what happens to light beams. And especially, I'd like to spend 1 minute on the physical interpretation. So I'd like to connect that to what we have said before, and in particular when we had this discussion about Ricci versus Weil lensings. So the thing is that in FLRW, which is conformally flat, that means there is a conformal transformation that can transform the FLRW metric to the Minkowski metric. So this is very obvious when k equals 0. So when k equals 0, this is just the Minkowski metric written in terms of the of spherical coordinates, and we see that we just have a transformation between Minkowski and FLRW by the scale factor. It is also true when you have k which is non-zero. It's less obvious when it's written like this. There are coordinate systems in which it is more obvious, but it's still true. So even for k equal for k non-zero, you have something which is conformally flat. And conformally flat, a geometry which is conformally flat has this property that the Weyl tensor is 0. So this is also why we call the Weyl tensor the conformal curvature. It's because it is the thing that is preserved when you are making a conformal transformation from one geometry to another. So the Ricci curvature is non-zero, but the Weyl curvature is 0. So given what we have said in the previous lectures, that tells us that when you have a light beam that propagates through a homogeneous universe, it is not distorted, there are no tidal forces, as we can expect from the symmetries of the model, but there is a global focusing. And this is true even if, when we draw some light rays in this coordinate system, this spherical coordinate system, light rays appear to be straight lines. So this is not incompatible with the idea that there is focusing of light beams. It's just an effect of coordinates that make you think that these are straight lines. But when you consider two light rays, neighboring light rays, and you consider and you look at the behavior of one of, well, yeah, their relative motion, they are actually focused. They are globally focused due to the matter that they encounter during the propagation. So this is the physical intuition. So there is no distortion of light beams. But there is global focusing. All right. So a way to write this thing could be just to use one of the equations that we have obtained in lecture 2. So illustrate, for example, if you look at the area of the light beam, so you remember that we had this relation that we derived for the square root of the area of the beam. Which was given by this Ricci focusing term minus sigma squared square root of A. This thing is 0 because there is no source of shear. And phi 0, 0, which is by definition minus 1/2 r mu nu k nu k nu. It is also minus 1/2, sorry. So I insert here the Einstein field equation. We get minus 4 pi j T mu nu k nu k nu. And if I specify here the T mu nu of the FLRW geometry, which is just, well, if I take, for example, a dust field universe, so no pressure, just dark matter and baryonic matter that is not relativistic, then what I get is simply this thing. squared. So this term is non-zero, and the intensity of its focusing effect on light beams is proportional to the density of matter, local density of matter. So you have more focusing in the past when the universe was denser, and the
also solid angle of your beam.
No, the omega squared is the frequency. And it comes from the k mu that we have here. Yeah.
So what happens with cosmological horizon? Because I expect in-going null rays to be diverging.
So you don't have divergent beams anyway. So this has no relation with the cosmological horizon whatsoever. It is just the way light beams, also how sources are focused by the mean universe. Right. So the physical interpretation that there is here, and this is very important, I think, to understand what are the approximations that we are making when we are studying light propagation in FLRW, is that you assume that when you have a light beam, it encounters some kind of homogeneous fluid. With density rho. So this is something, by the way, that motivated a few well, it motivated some debates since the 60s. It's Zeldovich who said at some point that, well, we are making this approximation and we are using this approximation, this picture that a beam is globally focused by the mean universe. So we use that in the interpretation of our observations. But when you think about very small light beams, they shouldn't really encounter so much matter. If matter is clumped into galaxies, dark matter halos and things like this, actually you could expect light beams to propagate through mostly empty regions. So that actually we should, in a realistic picture, we should say that this is much smaller in general than the average effect of the average universe, except for some light beams that get focused strongly when they meet a galaxy or a halo or gas. So yeah, we've had some discussions about that. And then it gave, Dyer, Rudder, Kontowski, and also my thesis was basically dedicated to studying this problem. It was criticized by Zeldovich. 64. Kontowski, 69, Dyer, Rudder, who proposed a partially field beam approximation to challenge this one, and this was 72, 73. Yeah. And you can also have a look at that. Okay. All right. And just to finish on the homogeneous universe, I'm going to give the expression of the Jacobi matrix in this. So when you solve the Zach's equations and you get the Jacobi matrix, so it is actually very simple. It's just the scale factor times chi. And delta. Very simple. Okay. So yeah, diagonal as we expect, no distortions. And this quantity, when you take the derivative of it with respect to the affine parameter, you realize that you really have some focusing on this. Alright, so that was about the homogeneous universe. Now let's go to the inhomogeneous universe. So what we call weak gravitational lensing.
Sorry, that is a relation with the Jacobi matrix. Does that depend on the dust assumption, or is it true for like?
No, this is completely general. Sorry, I forgot the K. This is in the case K equals 0. In general, you have the FK of yeah, sorry. That's also a remark, but given so what is usually presented is that people discuss the effect of the sign of K. You have people saying, well, so you see if K is positive, so you have this sign behavior that makes obviously kind of convergence of the beams, while when K is negative, you have a divergence of the beams. I want to insist on the fact that this picture is not physical. So the spatial curvature has no physical effect on the way light rays are propagating. Because the only physical source of focusing is this thing that has nothing to do with the spatial curvature. This thing, which is very conveniently written, is actually an artifact of the fact, well, it's a happy coincidence, it is due to the conformal invariance and things that gives this kind of interpretation, but this interpretation, again, is just geometrical, it's not physical. Source of focusing is just local density. The thing is that when you apply when you insert Friedman equations in that, you can replace rho into a function of spatial curvature and things like this, and the Hubble parameter that disappears when you go to the conformal metric. But there is no physical effect of focusing or defocusing of spatial curvature.
You're saying there is no measurable effect?
I say that, so there is a measurable effect in the way that you can constrain spatial curvature in the way that, for example, the distance redshift relation is behaving. I'm just saying that it's not directly spatial curvature that bends rays. It's not that. This is a wrong interpretation of the effect of spatial curvature. The thing is that when spatial curvature is bigger, to have the same Hubble rate, you need to have a smaller or bigger rho, and this is that which can be considered an effect of spatial curvature on density.
You're saying it's the matter of the beam that does the bending?
Yes, it is. Okay, it's geometrical. K has no direct effect on light bending. And this is because spatial curvature is just a quantity that emerges from the choice of a given coordinate system, a given frame. There is nothing physical in spatial curvature. Alright, so let's go to weak lensing. So weak lensing consists of the small distortions of light beams due to the large scale inhomogeneities of our universe. So this is distortions and small distortions of light beams and images, therefore, generated by the large scale inhomogeneity of the universe. So to model the large scale inhomogeneity of the universe, we usually work with perturbations with respect to the FLRW metric. So modeled with perturbations with respect to FLRW. So I'm going to specify a model and not, for example, I will consider from now on that k is 0, just for simplicity and also because it seems to be what is measured in the real universe. And so the metric that I'm going to take is this one. So we still have our a squared theta. We have one minus a plus, remember. Yeah. So, in this form of the metric, I have gathered all the spatial parts into a Euclidean-like metric, 3D Euclidean metric here. So I consider that k equals 0. I neglected vector and tensor modes. So I will not take into account the effect of vector modes or gravitational waves in the gravitational lensing. And I also considered that the anisotropic stress of matter contents is negligible, so that the two gravitational potentials, scalar Bardeen potentials phi and psi, are identical. Stress. Alright. So this is a very Newtonian-like metric in this case. And the Bardeen potential is very close, it matches on small scales the intuitive Newtonian potential. So when now you're studying light propagation through this metric, using the same trick, you eliminate the A and you just look at what would be the perturbation of light rays and light beams in just some, a weakly perturbed Minkowski metric, then what you can show, and I will not do the calculation explicitly, but you can do it as an exercise, it would be size 3, I think. Yeah, maybe. So the Jacobi matrix, in this case, is the following. So you have first term like this, and then comes a perturbation So the perturbation of light rays and light beams, infinitesimal light beams that is encoded in the Jacobi matrix comes as a line of sight integral of the second derivatives of the gravitational potential. What I call d orthogonal here is actually a screen derivative. It's a derivative in the direction of the Zach's vector in the background. So because here it's worked out at first order. Yeah, so I should have said it, but this is the Jacobi matrix at lowest order in phi. So the first thing that you can notice is that it is a symmetric matrix in this case. It's not obvious. I mean, this in general D is not symmetric. You can have rotation of light beams in general, so the rotation of the patterns of the images with respect to the polarization. This is what it would, antisymmetric part would mean. But now you have potentially non-scalar, of course, non-scalar components of T. So you can have distortions of light beams. So usually, in recleansing, we introduce another matrix which is called the Amplification Matrix, and which represents the Jacobi matrix relative to the background one. So you introduce this thing, so write D equal D bar A. So this would be an FLR W. And this is something that we call the amplification matrix. So yeah, I should have put a bar here to say that we consider the background here. And this is the amplification with respect to the background. It's actually a name which is not very well chosen, because it is the contrary. When the determinant of A is bigger than 1, then you have demagnification, and so this should be actually called more the de-amplification matrix or the demagnification matrix. Yeah. So when you introduce this matrix, then you decompose it the following way. So again, it's just a standard decomposition between the trace and trace-free part of a symmetric matrix, where kappa here is called the convergence, and gamma is called the shear. So be careful. This is not to be confused with theta and sigma that we introduced in the previous lectures. So remember that those quantities represent rates of deformations of the light beams. They are a deformation, well, per unit, well, when you go per unit, no, not per unit, but they are a derivative, they are kind of derivatives, logarithmic derivatives of those quantities, if you want. So the convergence tells you how, again, light beams, what is the net focusing of light beams, and shear, what is the net distortion of images. Right. Also another remark here about the expression of A. So it's only sensible, so this decomposition of A is only sensible for weak distortions. So when working at order 1 in perturbations. even if you can always decompose a symmetric matrix this way, when you have kappa and gamma that become of the order of order 1, or when they are not much smaller than 1, they will not directly represent the net focusing of images, or net magnification of images, or in the net shear. Actually, if you want a completely general decomposition and that is geometrically adapted to what you are studying, you need to introduce something a bit more complicated with a rotation matrix, a unitary matrix, which would be the exponential of traceless matrix, things like this. So keep in mind that this decomposition and the meaning of this gamma 1, gamma 2, kappa are just sensible when you are considering some very weak distortions. And by the way, so how can we interpret that? So you can make the same game as what we did when we considered the decomposition of the untitled matrix. Consider a given circular source and see how it is distorted by the amplification matrix. So, this would be for the interpretation of kappa and gamma. So, playing the same game. As when studying RAB. So you will realize that if you are taking a circular source and that you are applying a given kappa, will have some isotropic focusing of your so this would be the source, this would be the image, some magnification, global magnification of it, and if you are taking gamma 1, gamma 2, then you have a distortion, elliptical distortion of it, where this angle, theta for example, is such that so gamma 1, gamma 2, and actually it's not this angle, this one. To be checked for the sign, maybe it's a minus theta, and you have a small down here. It's not really important. What is important is that you have two numbers here, that the proper axis of the matrix minus gamma 1, gamma 2, gamma 2, gamma 1 will be given by this theta or maybe minus theta according to such a relationship here. So again, kappa, net magnification, gamma, net distortion. Right. Now, what I want to talk about is this. So, I would like to discuss slightly more the expression of the convergence. The convergence, so So you see, if you're taking the trace of this matrix, you are getting 2 minus 2 kappa. So it's taking the trace of this expression, you can get the expression of kappa. And what you show, therefore, is that kappa reads the following thing. In a good approximation, where delta is density contrast. All right. So this comes from the fact that when you're taking the trace of that, what you're getting is here a transverse Laplacian of phi, which is almost related to the density contrast by the gravitational dynamics, by the equations for cosmological perturbations, with the small thing that you have actually a transverse Laplacian, not a full Laplacian, so there is some longitudinal derivative that is missing. But the good thing is, with this integral here that you have over chi, you can actually add it and realize that there can be a small correction, but it will be negligible compared to what you have here. So it comes from, so using the fact that you integrate over chi here, you can insert the missing derivative and in the end recover a full Laplacian and transform it into a density contrast. And here we see again a quite good say interpretation of what's going on. If the line of sight that you are considering is going through overdense regions, then delta is positive, and therefore you have, oops, yes, yeah, sorry, it's a plus sign. So when delta is positive, the mean delta over the line of sight is positive, then you have a positive convergence which magnifies your object, or your image. When you are going through an underdense region, so when delta is negative, then you get a negative convergence and an image which is smaller than what it would be in a homogeneous universe. So it is less focused than in the mean universe. Okay. But there is some, so apart from, there's just a physical interpretation, geometrical interpretation of it. This equation is very interesting because it gives you a direct relation between something that you can potentially observe, the magnification of images, and the density of the universe, so the distribution of matter in the universe. And in particular, you can see that the correlation function of kappa will be directly related to the correlation function of delta. So measuring the power spectrum of kappa is indirectly measuring the power spectrum of density in the universe. And this is why this relation is also very important. So this is a direct relationship between an observable quantity and the distribution of matter in the universe. On large scales, of course, because again, this has been derived in the context of cosmological perturbation theory at lowest order, so this applies only when you have some weak perturbations. Even if its domain of validity is much wider than what we could expect. delta can be actually quite large, and this then still be applicable. Problem is, well, so yeah, so for example, measuring kappa can give you information about the power spectrum of the density contrast, and therefore of the computational potential, and tell you information about the primordial universe. So the problem is, kappa is actually very hard to measure directly, because usually you don't know what is the intrinsic size of the objects that you are measuring the images of. Right? To measure kappa, you need to know both things. You need to observe objects, but you need to know what are their sizes. So that's why actually people are not, in wavelengthing, not measuring directly the convergence, because it's roughly impossible. Well, there are some tricks, but it's very hard. But people are measuring the shear. So shear, this you can measure it, because you can do statistics. You can observe galaxies and say that, well, those galaxies, even if they have an intrinsic ellipticity given distortion, on average, those ellipticities should vanish on the sky. If you take a big sample of galaxies, you take the ellipticity with their given axis, you average over that, and you should get 0. But if you have shear, then you get some distortions that are coherent over the sky. That because they are related to the distribution of matter. So the solution, so as I said, kappa is hard to measure because we do not know intrinsic size of objects, sources. But gamma can be statistically measured. And the picture is actually the best to understand that. So suppose you have an area of the sky in which you have no lensing at all. So you can expect your galaxies to have random alignments like this. Yeah. So with no alignment. But if you have a big, say, cluster of galaxies or big bunch of matter that is causing gravitational lensing, what you're going to see something which looks more than that. Because of the shear effect created by this spot of matter here. Okay, you have some coherence, alignment of images. And using this intuition, what you can do is also to calculate the power spectrum of shear. So you calculate the power spectrum of the observed ellipticities, and that gives you the power spectrum of shear. Right, so just to give you the idea, if epsilon is a complex number that gives you the ellipticity of a galaxy, so it's a complex number whose whose absolute value gives you how elliptical the galaxy is, or the image is, and the argument gives you the angle on which this is defined. So you can always write that epsilon of the image is epsilon of the source, so the intrinsic one, plus gamma. So this is true if the ellipticities are small and gamma is small as well. So this is why you get this additive thing. So intrinsic ellipticity. This will be observed ellipticity. And when you take, say, calculate the correlation function of this thing, so you'll have a few terms. Right? So if you assume that there is no intrinsic alignments of the ellipticities of galaxies, then this thing vanishes, right? Because the ellipticity of a given galaxy at one point is not correlated to the ellipticity at another point. If you assume also that the ellipticity of galaxy is not correlated with shear, which is even more reasonable because there is no reason why the alignment, why the ellipticity of a galaxy would be correlated to the way everything is distorted by the mass in between. So those two things are zero. And therefore you have that this observable quantity statistically is equal to something that you want here. The power spectrum of the correlation function and therefore the power spectrum of the shear. And then there is a last key point which is the missing element. Because remember that what we would like to know is that it's a great thing called the Kaiser squares theorem. So, I forgot the date, the 80s, 90s, something like this. Which is that the power spectrum of the shear is the same as the power spectrum of the convergence. And this is a key theorem because you see now we have the whole picture. We can measure the power spectrum of the shear from the power spectrum for the statistical correlation of ellipticities of galaxies, something that we can really observe. And then this tells us directly the power spectrum of the convergence, and therefore, through this relation, the power spectrum of the density perturbations. So that's the key idea of weak lensing, measuring distortions of galaxies and using that to constrain the power spectrum. Yeah.
So what are the underlying cosmological assumptions?
The underlying cosmological assumption is the fact that we are considering a metric that I gave at the beginning with just a scalar potential. Things that you have is, it's actually quite intuitive in some way. We have just a scalar that is responsible for everything, all the distortions. And we separate those distortions between some global focusing and some distortions, but they are not independent. We know that they cannot be independent because they come from the same matter distribution that is only at a good level of approximation represented by a single potential phi. So yeah, this comes from the fact that that all those lensing phenomena kappa and gamma, all those are generated from a single potential.
So are you assuming also just first order still?
Yeah, this is first order. Yeah.
But highly specific to this setup?
So I don't know how this is. Yeah, I've never studied in detail this issue about what are the limits of this thing. What is the domain of validity of this thing? So, for example, how much is this relation violated due to the presence of vector? Vector modes of perturbations or tensor modes. If we go to, say, levels of approximation that are better than that, do we still have something that looks like that? So this is actually something that I don't know. Domain of validity. But in this context, at least it works. It's more.
So this convergence formula, does that depend on the equation of state of something? Is it pure dust?
Oh, that's true. So again, using this thing, when I replaced the Laplacian by this thing, I used the dynamics. So I used the equations for perturbations. So here there is the delta phi equal 4 g a squared delta rho. In this thing. Yeah. So if you change the dynamics of the formation of structures, then this gets modified as well. Yeah. Okay. What else can I say about weak lensing? Well, what I can say about weak lensing is that this is not the complete end of the story. So this is the standard picture, and big surveys that are I mean, like currently CFHT lens, or even Euclid, DES, all of them, they are using mostly this technique based on correlation functions. But there are some new propositions that emerged to use higher order statistics of the shear and ellipticities. Because here, actually, when you're doing that, you're losing a lot of information. You're just constraining the data, or using a part of the data that corresponds to the second order statistics, two-point correlation functions. So people started using some more general statistics. For example, the shear peak method is something that goes beyond this technique. And that could be quite promising. There are some forecasts that show that you can get better constraints on the cosmological parameters. Oh yeah, talking about the cosmological